Alright, everyone, I'll show y'all how to make your graphs for the Jominy lab. And so group each group got a different steel, and you did the Jominy end-quench test, and now the entire class will compile the data and make their memo. In the memo, it specifies this output technical memo, blah blah. Indicate which alloy would provide the deepest case, 35 HRC or above. And so we took our measurements in HRD. So if we kind of look for the rough conversion, 35 HRC is about 52 HRD. And so in your data, some of the steels didn't even get 52. So I would say just scratch that and change it to HRD just for the sake of the lab. It's the same idea though. So with the data, I wanted to add this little case step column. Um, you'll see why later. All right, so let's make a plot. We're gonna do scatter with smooth lines. And so select data. We're gonna add an entry. So first, let's do 1018. Do this position. Let me copy this. So we're gonna be repeating it. And then 1018. Okay, next, do 4140. Copy, paste, tab, select 4140. Okay, add 1045, paste, tab, copy. Okay, add 8620, paste, tab, copy, and done. Okay, so with this, here's all our data. You're gonna want axis titles, a chart title, and a legend. And so there you go, the graph's done. But there's a little bit more that I want y'all to do. Right, so on this X right now, this is the position. And so make sure you have your units position in inches. The Y is the hardness. We'll do that in HRD. And then the title, you can call it Jominy Hardenability Curves. And there you go. So this has position, but what if we want to graph the cooling rate also? And then we're talking about this case depth, and it's usually this like straight line across. Um, so how can we show that on the graph? So let's right click it, let's select some data. We're gonna add, let's just say a case or case requirement. The X values, let's choose the cooling rate. And then this case depth column. So okay, right now the graph looks weird, but just stay with me. We're gonna change this series chart type. Okay, actually hold off on that. Over here on the right, plot series on, we're going to choose a secondary axis. And then with that, you can change the chart type. Instead of a scatter smooth, we'll just do a line. And then with that, come over here. We don't want a secondary vertical, we want a secondary horizontal. And so you can see that K-step line is there. And then up at the top here, we need an axis title for the secondary horizontal. We have our cooling rate in Fahrenheit per second. These points, I don't know why it does this, but they get spaced out even though you don't want them spaced out. So you just have to kind of put them there, and then this extra line, you just have to get rid of some of these. And there you go. And so now it's just making the plot look however much nicer you want it. And so we can bold this, make it a little bigger to see. Can bold that. It's kind of getting washed out. Uh, can bold that and bold that. And then if you want to like change the color of these, come in here, change their outline. Say you want that case line to be red, can make it red. Let's say you want the 1045 to be blue, can make it blue. Let's say you want 1018 to be some sort of gray. You can do that. All right. And it's got the position, the hardness, you got your title, cooling rate is there. You've got your legend. You can maybe mess around with this, how to get rid of this empty space. I don't want to troubleshoot that live. Uh, yeah, no, I'm not gonna worry about that. But anyway, so we'll move this chart to a new sheet, call it sheet two, I guess, or whatever. And then with this, you can print it to a PDF and draw on it. So, um, there you have it. There's your graph, right? And so you can see here, the 1018 case depth is only that big. And then if you look at 1045, we're just adding carbon to it. And the case is going to be about that big. Okay, that came out bad. It's going to be that big. So we see adding carbon will increase the hardenability of steel. But if we look at 1018 and 8620, not much in, not much of an increase in carbon, but if we look at the hardenability, we see an even bigger increase. So it turns out the alloying elements will have a stronger influence on the hardenability than carbon. But if you add both alloying elements plus carbon, you get 4140, where it doesn't even go below the case requirement. So which of the steels will have the like largest case? 4140, because it's high carbon plus an alloy steel. Which one will have the lowest? 1018, low carbon, plain steel, not easy to harden. And then second, we'll have 8620. It's the other alloy steel. And then third, 1045. So number one, number two, number three, and number four. And so if we look at 4140, difference between it and 8620, 4140 has a little bit more chromium. And chromium will help with that hardenability. And 4140 also has more carbon than 8620. 8620 is known for having nickel. That's its difference from 4140. Less chromium, less carbon, and more nickel. And so nickel will have its own properties. And do these results make sense? Well, when you're a senior and you're taking fundamentals of engineering, you get the FE handbook for the fundamentals exam. And in the material science section, they have a hardenability subsection. And if you look at it, it looks just like what we got here with our data in the lab. So down at the bottom, the plain steels, low hardenability, and then the alloy steels are up at the top, high hardenability. And then you can see as you increase carbon, you see an increase in that case step size. One thing to note as you come back to this, notice that 1045 and 4140 start in the same spot. 1045 is a little higher because it has more carbon. So the carbon content really affects the surface hardness, right? Because the surface got quenched. And so you see they'll start at the same spot, but the drop off is way different. 4140 is a slower decrease while 1045 drops off very quickly. And you see the same thing with 1018 and 8620. Right. And so this is neat. You'll see if you look at 1060, all right, higher hardness than 4140, but 4140 is much easier to harden than 1060. And I think that about sums up what you need to deliver in your memo. Um, all right, yeah. Jominy Lab. Uh, all right, one more thing I wanted to add. What material would be better for a part that you want to be case hardened? So remember back to the case step lab, you looked at position versus hardness, and you saw it dip down and then dip back up. And the idea is that like if you have a gear tooth or something, you want a thin, hard layer on the outside, but the inside you want it to be soft, so it's tough and won't fracture or crack or something like it won't be brittle on the inside. And so the idea is you want a quick drop off. You want it to be hard and then soft. So what would be better? Something with a high hardenability that forms a deep K-step or something with low hardenability. And you would think, oh, the high hardenability is better because it'll form more K-steps. Well, no. Sure, it'll be more K-step, but it'll be more brittle. All right, so this would be like a low hardenability gear tooth versus one with high hardenability. It would be like a bigger chunk or a thicker case. With a case that thick, it's going to be very brittle. It turns out you don't need that much case thickness. Something with machine elements and you see stress below the surface and yada yada yada. But yeah, the idea is you want hard and then a quick drop off. Because if we were to say like we need 40 HRC, the alloy steels, look at this, up to almost 2 inches. 2 inches of a case depth is way more than you need versus something like a 1020 forms this case that we see here with a nice quick drop off. Right, so it's hard at the surface and then tough in the middle. So also you can look at the 1060s, very hard at the surface and then drop off. Right, so what would be better for a component that you want to case harden? You would want a low hardenability steel so that the case isn't too big. So yeah, I just wanted to add that.